Well, welcome everyone. And we're very excited to have everyone joining us. This is going to be basically the second annual Phi Tau Sigma research competition. It is sponsored by Phi Tau Sigma, and it's a competition that we kind of developed last year as a way for all Phi Tau Sigma members to participate in a competition among themselves, even though they may have presented uh, their research at different meetings. So let me switch this over to slideshow. Right. First of all, I want to thank our judges for today. So we have Amin Ozan from University of Georgia, Vishal Manjunatha, Clemson University, Ali I'm sorry, Ali, Ubi to Glory, sorry, University of Arkansas, Shifwan Wan, University of Platteville, Ram Shrestha, University of Nebraska-Lincoln, and Jacob Toole from Northwest Missouri State University. Thank you for all our judges and contributing to this competition. We really appreciate it. Okay, so just a little reminder, I think probably everybody here is Phi Tau Sigma members, but if there's somebody joining us, hopefully they are, that are not Phi Tau Sigma members, just a little bit about the goals and the mission of Phi Tau Sigma. And it is the Honor Society of Food Science and Technology that honors and elevates the achievements of students and professionals in food science and technology. As I mentioned previously, this competition is sponsored by Phi Tau Sigma. So we have 6 finalists that will be giving their presentation today. Just as a reminder, it's 3 minutes for their presentation. And is it 2 minutes, Fanbin, for questions? Yes. Okay. And the questions will all be from the judges. So after the student gives their presentation, they will have the opportunity to basically turn on their mics and ask the finalists their questions. Okay. Any questions before we start from either the judges, the finalist, any of the audience? Okay, I think we're ready to go. So our first student presentation is going to be from Jody Allen, who is with the Department of Animal Science at the University of Connecticut. Her presentation is the efficacy of eugenol nanoemulsions in activating Salmonella enteriditis on broiler chicken skin to enhance product safety. And Jody presented her research at IFT First in Chicago, Illinois this summer. So go ahead and get started. I'll give you a minute. So whenever you're ready, Jody, go right ahead.
Thank you for the introduction, Dr. Bolston. Many consumers are not aware that their favorite chicken products may harbor Salmonella bacteria, a major poultry-associated foodborne pathogen causing millions of illnesses every year in the United States due to the consumption of contaminated poultry products. And in general, chickens act as a reservoir host wherein the pathogen colonizes the ceca of broiler chickens, leading to product contamination during slaughter. However, to reduce salmonella contamination on poultry products, post-harvest strategies are integrated with minimal antimicrobial effect. And therefore, this situation warrants the development of a novel disinfection strategy to control salmonella on poultry products. And therefore, currently I am investigating the anti-salmonella efficacy of a generally recognized as safe plant compound known as eugenol obtained from the buds of clove. And I am developing nanoemulsions of eugenol oil using gum-arabic and lecithin as emulsifiers to overcome its low solubility in water. Therefore, the objective of my study was to investigate the efficacy of eugenol nanoemulsions in reducing salmonella survival on poultry products. To achieve my objective, chicken skin was inoculated with salmonella and immersed in water containing eugenol nanoemulsion or eugenol oil at different concentration levels up to 4 hours at 4 degrees Celsius. And after treatment, the surviving salmonella was enumerated on the skin sample. We also incorporated parasitic acid as an industrial antimicrobial control, as well as gumarabic and lecithin as an emulsifier control. The results showed that eugenol oil in its nanoemulsion form at its highest concentration of 1.25% was effective in reducing salmonella on chicken skin by approximately 3 log CFU per sample after 4 hours of treatment. And it was the most effective treatment as compared to salmonella-infected skins that were immersed in water or water-containing emulsifier or eugenol oil. I would also like to highlight that eugenol nanoemulsion was the most effective treatment as compared to parasitic acid, and it reduced the pathogen by an additional 1.5 log CFU. To conclude, these results will present an alternative antimicrobial strategy to reduce salmonella survival on poultry products, and thus this presents a wholesome and a safe product for human consumption. Thank you for listening.
All right. Thank you, Jody. And so now we have 2 minutes for questions from the judges.
Maybe I will start. So thank you for the presentation. How relevant do you think this is 1.25% application for the industry?
So thank you for the question. So the 1.25% concentration is relevant for the industry in eradicating salmonella on poultry products. So currently the industry is incorporating parasitic acid at a concentration of 200 ppm. However, it's been previously shown that it's not completely effective in killing it on the skin sample. So therefore, we are testing different concentrations that will have similar or better efficacy as compared to parasitic acid.
So do you think this concentration may have an impact on the quality of the chicken, like flavor and other things?
So currently we haven't done any organoleptic properties or analysis to see if this concentration will impact the sensory profile of the chicken meat. However, we have conducted color experiments as well, and we have shown that there is no impact on skin color. But in regards to other analysis organoleptic properties, we still have to explore that further.
Thank you.
You're welcome.
Question for Jody. Nice presentation. Have you looked at the economical feasibility? Eugenol is a bioactive compound, so it's going to be really expensive to incorporate in the industry. So what are your thoughts on the economic feasibility?
So thank you for the question. So the overall aim of incorporating eugenol into nanoemulsions is to reduce essentially the cost, because eugenol in itself is very a volatile compound, and also for it to have an antimicrobial effect, it needs to be a higher concentration. So in order to have it be reduced to the economy, we incorporate it as a nanoemulsion to get less of a concentration to have more of a greater antimicrobial effect. And thus, this will potentially reduce the cost if it's in its nanoemulsion form, as compared to if it's in eugenol oil form.
How does it compare with peracetic acid treatment or other current treatments used?
So in regards to other treatments in regards to parasitic acid, so as you can see from the graph displayed on the right of the slide, it has better antimicrobial efficacy after up to 4 hours of treatment as compared to parasitic acid. It reduced by an additional 1.5 log CFU. So in regards to like the pricing, we have to do like a cost benefit analysis to further come to a conclusion of its economic feasibility in the industry.
All right. Well, thank you to the judges for the questions. Unfortunately, we need to kind of keep moving along, but very good questions. And thank you, Jody, for your presentation.
You're welcome.
Okay. Okay. Our next presenter will be Raina Marie Buenavista, from the Department of Grain Science and Industry at Kansas State University. Her presentation will be on the air classification of navy beans into protein-rich powder. And this is research that she has presented at the Conference of Food Engineering in Seattle, Washington. All right. There you go.
Imagine this. You are at the grocery store looking for a high-protein food to fuel your week. You went to the meat aisle, but then you saw something else. Rows of plant-based protein options. Beans, lentils, chickpeas, and all sorts of new plant-based products promising high protein and sustainability. People are drawn to it for several good reasons. It's better for animal welfare, nutrition, and of course, the environment. But here's something surprising. If we don't change how we produce plant proteins, this growing demand could actually harm the environment. Most plant proteins today are made using wet extraction. This method does a great job at isolating protein, but it comes with a cost. It uses large amounts of water, harsh chemicals, and energy, ironically contributing to the very climate issues we're trying to solve. My project uses a more sustainable method called the air classification. Instead of using chemicals and water, this technique uses only air to separate protein from other components. First, the beans are ground into a fine powder. Then, the powder enters an air classifier, a machine that uses circulating air to sort particles based on size and weight. Now, how do we separate something as tiny as a protein from the rest of the flour? Well, proteins are lighter and smaller compared to starch particles. The air is just strong enough to carry the protein upwards, while the heavier starch settles at the bottom. In my research, I optimized this process by fine-tuning the airspeed and adjusting how the powder flows through this classifier. This is important because different grains have different properties. If the air is too weak, some proteins will be lost. If it's too strong, we might end up with some impurities such as starch and fiber in our final product. But take note, there's always a trade-off. We can either get a higher protein yield with some impurities or a purer protein but in a lower amount. Using this method on navy beans, I successfully increased the protein content from 21 to 45% without a drop of water or a single harsh chemical. This only proves that we don't have to choose between sustainability and efficiency. By adopting cleaner methods like air classification, we can produce high-quality proteins while protecting our planet. Remember, we are not just making choices about what to eat, but we're also making choices about how our food is made. Thank you.
All right, thank you very much. Okay, now we have time for 2 minutes for questions from the judges.
Maybe I will start things off. So what was you have this 45%, so is it like the purity you obtained?
Yes. 45% protein content of my final navy bean high protein powder.
And what is the rest, 55% here?
So it is also composed of different other components because our major goal here is to increase the protein content from the initial one because it can be used as a concentrate when we use it into other food products. And so by retaining some of the components, we're also having a very good functionality in terms of integrating it into other food products.
Sounds good. So what was the initial concentration and this final question?
It's 21%.
Okay, sounds good. Thank you.
Thank you.
Thank you, Rania, for nice presentation. I have a question regarding, is there ways to increase or optimize the air classification system? Is there any other additional tools that we can incorporate in air classification to increase the yield of the process? And can you compare the yield of the process between different, like the conventional water-based processing and the air classification?
Yeah, so in terms of the tools, it's not necessarily about the tool. We can also optimize it based on the particle size of our starting material. Say, for example, we load flour into our air classification. So unlike the normal flour that we use for air classification is very finer than the normal flour, which is about less than 212 microns normally. But for this one, it's usually way below, like around 40 to 45 microns. This we ensure that the size of the starch particle is somewhat similar to the size that we're trying to separate. So if the starch particles is about 22 microns, we're targeting about 35 to 40 microns so that when we separate them based on size and weight, starch particles are kind of separated from the protein because protein are about 6 to 10 microns in size. And so based on what you said about comparison, in terms of comparison, we can do that by getting a wet extracted protein and comparing the functional properties of the dry method as compared to the wet extraction. But most studies have compared several proteins, and mostly native functionality of the protein is actually preserved with the dry method because we're not using harsh chemicals and other harsh conditions. That example is high heat in wet as compared to the wet extraction method. So in terms of functionality of dry method is better than a wet extraction method. In terms of cost, there are limited studies about the cost for the air classification and wet extraction. However, based on the resources that you need for wet extraction, it's clearly that it's a more sustainable process and less resources needed. Thank you.
All right. Well, thank you. And we do need to move on. So thank you again, Rania, for an excellent presentation.
Thank you.
Okay, our next presenter will be Thirindu Trishan Dapana Duraj, who is from the Department of Food and Bioprocess Engineering at Louisiana State University. Presentation is a combination of xanthan gum and L-lysine HCl solutions as a potential phosphate substitute for frozen white shrimp. This presentation was presented at IFT First in Chicago this summer. Okay, so let's go ahead and get started. Thirindu, yeah, there you go.
Okay. Shrimp without phosphate? I would say yes. Imagine a world without shrimp. Hard to believe, right? This industry is worth over $1.3 billion and support 15,000 jobs in Louisiana alone. But there is a problem. Shrimp spoil very fast due to their high moisture content and delicate structure. So to slow this down, we freeze them. But does freezing fully preserve shrimp quality? No, it can still damage structure, reduce yield, and break down proteins. That's why the industry relies on sodium tripolyphosphate and alkali metal compound to preserve the frozen quality of the shrimp. It helps, but growing health concerns, environmental impact, and stricter regulations are raising public skepticism. Without a natural alternative, we risk losing consumers' trust, shrimp exports, and industry profits. That's where our research comes in. We hypothesize that xanthan gum and L-lysine in combination, both natural, safe, and functional compounds, can retain moisture, prevent protein damage, and maintain processing yield of shrimp, just like sodium tripolyphosphate. Here's what we did. We prepared xanthan gum and L-lysine solution 0.5 to 1%, used ultrasound-assisted homogenization, soaked shrimp for 3 hours, then froze and stored them at -18 Celsius for a week and 12 weeks for TBAS analysis. After that, we tested water holding capacity, yield, protein stability, and lipid oxidation. What we found, interestingly, 1% xanthan gum in combination with 0.5% L-lysine maintain water holding capacity and processing yield comparable to 4% sodium tripolyphosphate, proving its effectiveness. How? Because xanthan gum could act as a cryostabilizer, immobilizing water, reducing ice crystal formation, while L-lysine could enhance hydrogen bonding and van der Waals interactions, preventing excessive protein denaturation during frozen storage. TBUS analysis showed significantly lower lipid oxidation, showing the synergistic antioxidant effect of both xanthan gum and N-lysine monohydrochloride. So what does this mean? In conclusion, we now have a natural effective sodium tripolyphosphate alternative, keeping shrimp fresh, safe, and high quality without synthetic additives. It's a win for the industry, consumers, and sustainability, because why compromise when nature already has the answer? Thank you.
All right, thank you very much. We have a few minutes for questions from the judges.
I can start off. Very nice presentation. Could you just describe what the base mechanism for sodium tripolyphosphate and other alkaline compounds, how do they improve frozen shrimp quality?
Yes, thank you very much for the question. If we take sodium tripolyphosphate, it's a basic compound, like the pH value is usually like around 9 to 10. And when we have this high pH, myofibril proteins are responsible for water holding capacity of shrimp. And when we increase pH, because of the the repulsive forces, or when we increase in the pH, the negative charge can be increased. So it means there can be some repulsive forces making degrading, or not degrading actually, repulsive forces making more space to bind water with this microfibril protein. And at the same time, sodium tripolyphosphate can stabilize the muscle structure. If you see this microscopic image, the sample treated with 4% sodium tripolyphosphate, you can see the muscle structure is more stabilized, probably through the same mechanism as I mentioned, and acting as a scavenging agent, because sodium tripolyphosphate can help scavenging magnesium, calcium ions, that and also reduce the protein oxidation, which can make the protein like more tough. So those are the main mechanisms how sodium tripolyphosphate can improve the water holding capacity, thereby maintain the processing yield.
Thank you.
We have time for one more question.
I have a question. How do you compare the sensory attributes of this kind of treatment and the STPP treatment?
Yes, thank you very much for your question. Okay, sensory. Under sensory evaluation, we did not observe any significant difference of the taste or flavor compounds, but if we consider the color, usually sodium tripolyphosphate treated samples had more like red color, because as I said, the pH is very high in sodium tripolyphosphate. So probably it releases more astaxanthin to the surface just by degrading the protein structure, especially keratinoprotein. And the red color, if we analyze the color, usually color is quite high in sodium tripolyphosphate treated samples. But in our treatment, the pH is not that high. It's around 6 to 7. So redness is little low, but there were no significant difference between other sensory evaluation properties, sensory properties.
Well, great. Thank you very much. Great presentation. Okay. Our next presenter will be Gopinath Mummaletti, who is from the Department of Food Science and Technology at the University of Georgia. The presentation will be microplastics, interactions, and transformations during in vitro digestion with milk. And this research was presented at the Gordon Research Conference in Southern New Hampshire. So we will go ahead and get started.
Good afternoon, everyone. Thank you so much for the presentation, Professor. So every day we are consuming different kinds of food materials along with the milk for daily requirement of essential nutrients. Along with the nutrients, we may also ingesting the tiny plastic particles, which are microplastics, which are getting infiltrated into our food chain every day. So the microplastic contamination in food systems is becoming an emerging issue these days. And what happens to these microplastics inside our digestive system remains unexplored. So to fill this research gap, my research investigates how these microplastics transform during the digestion process, particularly how they are going to interact when there is a food medium like milk. So to conduct this study, 4 different plastics, mainly polyethylene, polystyrene, polypropylene, and polyethylene terephthalate, which are most common food packaging materials, are ground into a fine powder of 200 micron size using cryogenic grinder, and they are digested in the digestive fluids with and without the food medium, which is milk. And then we have analyzed the physical and chemical changes happening in the microplastics using FTIR, Zeta potential scanning electron microscopy, and GCMS analysis of digester was studied to detect the chemicals leaching from the plastics during the digestion process. So after the digestion process, there is a reduction in the Zeta potential values was observed, which is mainly due to the aggregation of the microplastics after the digestion process, as well as protein corona formation around the microplastics during the digestion process along with the milk. This suggests that this may enhance the interactions with the biological systems, potentially affecting its absorption and toxicity towards the biological systems. So in the FTIR analysis, there are new groups like hydroxyl groups and C-double-bond-O and amide groups were observed in the FTIR spectroscopy. So when the milk is absent in the digestion, there might be an interaction with the enzymes present in the digestive fluids, which shows the peak at around 1600 centimeter inverse. And when the milk is involved in the digestion process, the area of the peak increase, which indicating the interaction of microplastics with the protein. And when we have analyzed the digester to analyze the compounds leached during the digestion process, we have observed various kinds of chemicals like plasticizers, stabilizers, and other chemicals, which are mainly based out of phthalates and bisphenols, which are used in the chemical manufacturing of various plastics, which may create hormonal imbalances and potential health risk to the humans. So the leaching of these chemicals raises a large concern and long-term effects, including metabolic disorders and endocrine disruption. So this research underscores need for safer food packaging materials and better regulations to minimize the plastic contamination. And then further, the impact of nutrient absorption and toxicity in the biological systems needs to be studied. So the aggregation and chemical changes and leaching of additives from the microplastics raise the importance of health concerns, and to reduce human exposure, we need strict regulations and better packaging alternatives and increased awareness. Finally, every meal we consume could carry more than just nutrients. Understanding how these microplastics gonna interact with the food ensures a safer and healthier future. Thank you.
Right, thank you. See, we have about 2 minutes for questions from the judges.
Hi, Gobina. Why did you ground the plastics into 200 micron? Why did you select this size?
So based on the previous literature and epidemiological studies, we have came across different sizes of the microplastics, and we finalized it to conduct our research with 200 microns. And further, in my further study, I'm gonna use 50 micron sized as well, and also nano-sized plastics of 250 nanometers.
Oh, okay, thank you. That's great. Thank you.
I have a question, general question. Like, does the milk consumption of milk reduce the bioaccessibility of the microplastic in our digestive system then?
Still, this hasn't exploded, because when there is a protein corona formation because of the interaction of the microplastics with the proteins present in the milk, this protein corona formation might enhance the absorption of the microplastics inside the body, or otherwise, due to the aggregation of the microplastics, there will be increase in the particle size of overall microplastics, which may pass through the gut. Still, this is unexplored, and we have to explore it further in the real-time environment, like in vivo studies.
All right. Okay, well, thank you very much for your presentation, and we will continue on with our next presenter, who is Sandeep Paudel from the Department of Dairy and Food Science at South Dakota State University. The presentation will be the biodegradable films from alfalfa cellulose to extend the shelf life of strawberries. And this research was presented at IFT First in Chicago, as well as the Minnesota IFT Great Plains subsection also this year. So we'll go ahead and get started.
Thank you. How many of you drink water from plastic bottles? Yes, we all do. We all buy around 1 million plastic water bottles every minute globally, and almost 1 truckload of plastic waste is dumped into the ocean. And plastic production is skyrocketing, and it has already reached like 11 billion metric tons in 2022 and is on par with population growth, and so is the plastic waste. Even though we discard our plastic waste in the recycling bin, only 9% is recycled, 12% is incinerated, producing harmful gases like carbon dioxide and carbon monoxide, and rest ends up in the landfills and in the oceans. And during this process, it takes almost 1000 years to degrade, and it transforms into microplastics and nanoplastics. As my previous speaker also talked about the microplastics. And these tiny particles are hazardous to humans, animals, and the environment, affecting the ecosystem and killing more than 1 million species every year. Thus, it is urgent to sort out this problem. And if we see the total plastic waste generation, almost half of it is from packaging. Thus, it is important to develop plastic replacing packaging material. Hello everyone, I am Sandeep Paudel, PhD Food Science student at South Dakota State University. I am designing and developing eco-friendly biodegradable packaging films. Cellulose, a plant-based material, stands out as a strong candidate in using as a replacement for the plastics. And to make it more sustainable, we are using field residue of alfalfa forage since it is abundant, strong, stiff, and biodegradable. We are extracting cellulose using alkaline and bleaching treatments. It is then solubilized in zinc chloride solution, cross-linked with calcium ions, and plasticized with sorbitol to make film. Our prepared films are stronger than plastic films and also biodegrades in soil within 30 days. And these films also additionally possess antioxidant properties and then UV blocking properties, which are essential in preserving fresh fruits and vegetables. We tested our films in preserving strawberries, and the result was exciting that the strawberries shelf life was extended for 2 extra days compared to plastic films. Our zero waste approach lowers the environmental pollution and also provides an additional income to the farmers, adding $1 billion annually. Our research significantly contributes to the circular bioeconomy and sustainability. Thank you for your attention.
Thank you, Sandeep. Okay, we have about 2 minutes for questions from the judges.
So Sandeep, with this being a film, what's the rest of the packaging made out of instead of just that top initial layer?
Thank you for your question. At this moment, like we have like a film, so we were testing this in preserving strawberries using a glass jar. It was covered with the plastic films on the top, but definitely we are working to make it the wholesome packaging material in the future. We are working on that. Thank you.
Out of this film?
Sorry?
Like all of the packaging would be made out of the film, you're saying?
We are planning to do so, but at this moment we used glass jar. Glass jar was like covered with the like the control was like covered with the plastic films, and the test material, this alfalfa films was also used to cover those glass jar, and we are comparing those samples. Yeah. Thank you.
Other questions?
I have. What are the concentrations for your crosslinkers? Did you try or
Sorry, can you please repeat your question?
what are the crosslinker concentrations for the cellulose, like calcium ions? Did you try just one concentration or did you try different concentrations? How they did affect the results?
Thank you for your question. Here in this experiment, we used box banking design to develop the films. There were like different combinations. For example, your question was regarding the calcium ions. We used like 3 levels of calcium ions. It was like 200 millimolar, 350 millimolar, and 500 millimolar of calcium ions. And here we, after using the box banking design, we had like 15 different sample runs. Among them, we optimized and found out this concentration. It was like 461 millimolar, which gave like higher tensile strength and higher elongation at break and lower water vapor permeability, which was chosen as the best sample to be used. And we used that optimized film combination in testing like for the further properties. For example, biodegradability test and also for this shelf life study. Thank you.
Okay, thank you.
Okay, thank you very much. We'll now move on to our next speaker, Toshifumi Udo, who is from the Department of Food Science and Technology at the University of Georgia. His presentation will be on the impact of dynamic gastrointestinal conditions and food matrices on survival and release of encapsulated Lactobacillus rhamnosus GG. This research was presented at the Conference of Food Engineering in Seattle, Washington. Okay.
Thank you very much for introduction. Again, my name is Toshimi Udo. So, encapsulation of probiotics is a well-known strategy to enhance their effectiveness in the human body. So, the goal is to protect probiotics in the stomach and ensure their controlled release in the intestines. To test how well these encapsulated probiotics survive, researchers often use static in vitro models. However, these models do not fully replicate real digestion systems. In this study, we investigated how dynamic models and also food components provide a more realistic assessment of probiotic survival in the simulated digestive fluids. So for this, we encapsulated Lactobacillus rhamnosus GG in chitosan-coated arginate beads to improve its resistance to digestive conditions. Then we conducted 2 key tests. First, we compared static and dynamic digestion models to assess how continuous supply of digestive solution impacts probiotic survival and release. Second, we examined the effects of different food components in this study, including soybean oil, cornstarch, and casein on probiotic stability and release, which could be digested at the same time in the human GI tract. So our results revealed some important findings. First of all, dynamic models showed about 1 to 2 log CFU level reduction, lower probiotic survival, and rapid release than static models at both tested pH levels 2.5 and 3.0 of gastric juices, suggesting that traditional methods may overestimate the probiotics viability by ignoring the effects of digestive fluid supply shown in these dynamic GI models. Second, for food material study, casein significantly improved probiotic survival, likely by buffering stomach acid and providing additional protection. On the other hand, soybean oil caused severe capsule breakdown, leading to the complete loss of viable probiotics during digestion. So in conclusion of our study, my research highlights some key takeaways. First of all, dynamic digestion models demonstrate greater stress in the stomach and faster probiotic release in the intestine compared to the static models. Second, food components other than capsule materials strongly influence probiotic survival and release during digestion. So by understanding these effects, we can develop more accurate assessment and also probiotic delivery systems and therefore improve the design of functional foods for better health benefits in the future. Thank you very much for listening.
Okay, thank you very much. Okay, we have some time for questions for Toshifumi.
Yeah.
I have a question. Can you quickly discuss the difference between dynamic and static models?
Oh, yes. So in our study, we firstly started with very simple dynamic models, which simulates the continuous continuous supply of digestive solution using peristaltic pump at 2 milliliter per minute rate flow speed, as well as emptying the digestive fluid from the beaker at the same flow speed. So which can be seen as the circulation of digestive fluid during the digestion.
Thank you. Was it also mixed at the same time?
Yes, we using water shaking baths to maintain the temperature, as well as mixing all the fluid and the arginine beads uniformly during the digestion simulation. Thank you very much.
We have one more question for our speaker.
Maybe I can
Thank you.
follow anyway. Yeah.
Thank you for your presentation. I have a curiosity about how soybean will increase the dissolution of the capsule and the casein will do the opposite way. How it happens? What is the
Thank you very much for your question. Yeah, that's very interesting point. So we hypothesized that the intestinal juice includes lipase. So the included soybean oil will be degraded to glycerol and long-chain fatty acid. So it is known that fatty acid has a very weak binding property to calcium ions. So as it is assumed that the produced fatty acids may have some kind of creating property function to attract calcium ions, which are used for cross-linking arginate beads. So probably this would facilitate the breakdown of arginate beads much faster than other food materials and also control. So yeah, we are still working on the mechanism of this phenomena, but I think it's very interesting point. Thank you very much for question.
Oh, thank you very much. Okay, so that ends our presentations. So now it's time for the judges to come to, I guess, identify our winners. Okay.
So we have a tie on the second and third place, and I'm happy to announce that from the numbers we got, it's really competitive and it was very close call, and that's why we have a tie here on the second and the third place. So the first is Jody Allen, and then Toshifumi sharing the second and the third place. Congratulations to you. And in the first place, we have Tarindu as the first place in the competition. So congratulations to everyone attended. And so I think the second and third place will be sharing the 2 awards, basically average.
Yep, so I believe total awards was $600. So first place is 300, and then our 2 finalists that tied for second will receive 150 each. So great job. Thank you everyone for participating. Again, very excellent presentations, and it's exciting to see all the research that's going on and all that food science looks pretty good with all this great talent coming forward. So thank you again and have a great day.